Okay, next order of business. We're going to go over the unit load method. Now, the unit load method is probably where you're going to be tested on the most because it's very important. All right, it's one of the most important things in structures, and I remember I got tested on it a lot. So make sure you know it really well. So the best way to describe this method is by doing an example. Okay. So we have this system here, and we have to find, what's the question? What is the deflection at B? Okay, what is the deflection at B? Now, we got loads here, so we assume that this thing is going to go something like this. Boop, boop, boop. And then there's going to be a deflection here, delta B, right? You can just see that from logic. But to actually calculate this quantity is a bit different. Now, the way we'll do this is in a couple parts. First thing we have to do, we have to find the moment. Right, we have to find the bending moment across this whole beam. Okay, and the way we do that, if you remember, the way we find the moment is that we make a cut. Okay, we make a cut and we look at this cut. First thing you do before you make a cut, you have to have some kind of axis. You have to have some kind of coordinate system. You can start your coordinate system like this and call this the x-axis, or you can start the coordinate system like this and call this the x-axis. I'm going to start the coordinate system like this, and I will tell you why once we do it. Okay, so this is our coordinate system. We have x positive going to the left, and I'm going to make a cut somewhere in the middle. You have to make a cut somewhere in the middle, okay? And now we expand this cut, and we look at it. All right, that was terrible. Something like this. My bad. It's going to look something like this. Okay. And this is our cut. So this is what we're going to do. First things first. These are our forces, right? On our cut. And this distance, we're going to always call this distance x. All right? And obviously this is point B. So next thing we have to do, every time you make a cut, there's always two things that are going to be there. Actually, there's going to be three, but we're only going to focus on two. There's always going to be a shear force. Shear force is going to look something like this. We call it V. And there's always going to be a bending moment. Okay? Bending moment we call M. Okay. Our job now is to find this M and to find this V. And once we do that, we're basically halfway done with the game. Okay. So, how are we going to do this? Well, it's as simple as sum of the forces and sum of the moments. Alright, my bad. Okay, so sum of the forces, sum of the moments. We have a load here, right? And when we have a load, we have to first find the total amount of force in this direction. And we also have to find at which location this force is, right? Because since this is a distributed load, it's going to have a single line of action, right? And to find first thing first, we're going to find the total amount of force that this load is exerting on us. And the way we do that is we're just going to integrate it. Okay? So, the force, as you can see, it starts from 0 at the edge, increases to this value. Now, what is this value here? That's the question. What is that value there? Well, as we did in the previous video, we're going to have to use similar triangles again. And this is a common theme in this stupid structures class. So, here we're going to have to use all the information that's given to us. Here we have Q0. Q0 is the load at A. It's the load at point A. It's the maximum load. But we're interested in the load at point X. Right? Remember, our coordinate system starts here. So at point X is going to be right here. We're interested in what is this load. We're going to call it just Q. Okay? Or you can even call it Q of X. And the way we're going to do this, similar triangles, once again. Okay? So, we know that the ratios have to be consistent. So, we know that Q naught over L is equal to Q of X over X. Right? Pretty easy. And from this, we can solve for Q of X. Q of X is just Q naught X over L. Okay? Easy enough. Now, we found Q of x. This is Q of x right here. Q of x. And now what are we trying to do in the first place? Well, we're trying to find the total force exerted on this section right here. And the way we do that, well, is just a triangle. So 1/2 times base times height. So the total force, we'll call it capital Q if you like, is just going to be 1/2 times base, right, times base times height. And the height is Q of x. So Q naught x over L. And what does that give us in the end? It just gives us Q naught x squared over 2L. Okay? And now there's something that you should commit to memory before you take the final. Whenever you have a triangular load like we have here, your cut section force is always going to be quadratic. Okay? It's always going to be quadratic. Okay? And when you have something that's like a box, something that's rectangular, that means it's constant, it's a constant load, you're always going to have linear. It's always going to be linear in the cross section. Okay, so now that we have that, this is the total force that's acting on our member. We also have to know what is the location. What is the location of it? Now this is a little more tricky, but there's this thing you should memorize, that in a triangular load, let me just scroll down a bit here. In a triangular load, it's always going to be 2/3. Always going to be 2/3 away. Oh my god, what's going on here? It's always going to be 2/3 away. So somewhere right there. Because you can kind of tell that there's much more load here than here, so it's definitely can't be in the middle. So it's definitely somewhere to the left, and actually it's exactly 2/3 of the way there. So that means that this distance is simply 1/3 x. Okay? Since this is 2/3, this is going to be 1/3 x. And you should commit that to memory. Okay? So now, we know that this load exerts itself right here. This is the exact location of the load, and we know the exact amount of load as well. So, next thing we're going to do is we're going to sum the moments and sum the forces. Sum the forces in the y direction. What is that going to give us? Well, we have V going downwards, right? So that's negative V. And then we're also going to have this load going downwards. And what is this load? Q. So it's going to be minus V minus Q naught x squared over 2L equals 0, right? Equals 0. Because the sum of the forces have to be always equal to 0. That's the whole point. We're trying to find out what is V. So from this, we can see immediately that V is going to be equal to negative Q naught x squared over 2L. Okay, and what does this negative sign mean? This negative sign means that the actual direction is going to be upwards for V. And that's pretty obvious because this thing is going down, so V has to go up. Okay, next order of business. Let me scroll down here. Next order of business. Sum of the moments, okay? Sum of the moments about this left endpoint. Okay? Sum of the moments about this left endpoint. First of all, we have this bending moment M. And M, so let me just write here, sum of the moments about this endpoint is going to be equal to 0. And 0 is going to be equal to the sum of the moments. So M, this is a counterclockwise moment. Counterclockwise, we usually say it's positive. So plus M. Alright? And now we have to take into account this one. And this one you can see is going to be clockwise. So it's going to be negative. And then it's going to be equal to Q, which is Q naught x squared over 2L times this distance, 1/3 x. That's why it's very important to know what is the exact location of this thing, because you have to always multiply it by this arm. And this is equal to 0, so this means that M is equal to Q naught x cubed, right? X cubed over 6L. Okay, perfect. We're almost done here. Now, this whole video is about the unit load method, right? And what is the unit load method? Well, good question. I'll tell you. Let me just redraw this guy real quick. And this is our beam, and this is point B. Unit load method is very simple but powerful. What the unit load method does, you take away all the loads from the system. What loads do we have on this system? Well, we just have this triangular load. So we take it away completely. And what do we replace it with? We replace it with, you can guess, a unit load. All right? And where are we going to put this unit load? Well, we put this unit load exactly where we want to. And what do we want to find out? We want to find the deflection at B. So we're going to put this unit load at B. Okay? So that's the procedure. That's the procedure. You take away all the loads from the system and you replace them with a unit load, a load of magnitude 1 at the point in which you want to find the deflection. Okay? And we repeat the procedure. We make our x-axis. We make a cut. Okay? And that's it. So we have our cut. We have our block. And now we have a load here of magnitude 1. As before, we're going to have a shear force going upwards and we're going to have a bending moment. And as always, this distance is x. I'm going a little fast, but you can always slow this down if you need to. So, next things next, we have to find the sum of the forces in the y direction. What is that going to give us? V equals 1. That's pretty obvious. Sum of the moments is going to give us, what is that going to give us? Well, we have m going counterclockwise, so it's positive. We have 1 times x is going to give us minus x because it's clockwise, right? And this is equal to 0, so that means m is equal to x. And you know what? When you do the unit load method, this is pretty important. When you do the unit load method, instead of writing v and m, you're actually going to write v bar and m bar. Okay? Why do we write this? Well, we write this to distinguish it. So when we write m, that means it's the regular system. And when we write m bar, that means we're specifically dealing with unit load. Okay? So now that we have this, and now that we have this, we're almost done. How do we find the deflection, right? That's the whole question. How do we find this delta B? That's our question in the beginning. And how do we find it? Well, there's this formula, okay? And the formula says that delta B is equal to the integral along this whole path. So from 0 all the way to the end, which is L. So the integral from 0 to L of m times m bar over EI dx. Okay, this you have to memorize. Put it on your crib sheet. I don't care. What is E? What is I? Well, I is the cross-section moment of inertia, and E is the elastic modulus. They will usually give it to you in the form of, well, they can give it to you as numbers, but usually they will give it to you as symbols that you just include. Okay, so let us compute this integral now. We just plug in everything that we know. What is m? M from over here is q naught x cubed over 6. Q naught x cubed over 6L. That's m. What is m bar? M bar is just x. Pretty easy. And then we have to divide this whole thing by, you guessed it, 1 over EI. And we just need to integrate it. So this is going to, let me just pull out all the constants. This is going to be q naught over 6L EI. Integral from 0 to L of x to the 4th power dx. And this is just going to be equal to q naught L to the 5th, because integral of x to the 4th is x to the 5th. Q naught L to the 5th over 5, because this integral is x to the 5th over 5, right? And then we plug in L. So q naught L to the 5th over 5, 5 times 6 is 30, 30 LEI. We see 1L cancels out with this guy, so this is equal to q naught L to the 4th over 30 EI. That's your answer, sir. That's your answer. Okay, that was a pretty easy problem, but I just want to highlight you the steps. The next problem we're going to do is going to be a much more complicated problem, but this should be a good video about the procedure, okay?